have here Pascal Simon. He's an old friend of mine and also a friend of David. When we were in Geneva doing our postdoc, we met with him, and this collaboration started there, and then we had continuously making new projects and new things together, mostly on quantum physics because he's also a quantum guy. And now he moved to some Majorana physics, so maybe at some point we can also convert towards Majorana or towards Majorana quantum, whatever. So Pascal, he did his PhD in Paris in 1998 with Benoit Duzon. Then he did several postdocs in Canada, in Boston, in Trieste, many places. And then he moved to Grenoble with a permanent position in 2002. Then he stayed there for 6 years until 2008. Then he moved to Paris. He's now in the University of Paris Sud as a professorship, with a professorship position. And today he's going to talk about Majorana. Thank you.
Thank you, Rosa, for your kind invitation and introductions. And so today I would like to talk about Majoranas as was introduced. So maybe I switch a little bit the title. So Rosa asked me to do some kind of, let's say, large and broad introduction to the physics of Majorana. So I will try to compel with such demand as far as I can do. So let me first define what is a Majorana fermion. In short, a Majorana fermion is a fermion which is its own antiparticle. Fine. So first it's a fermion. So it tells you that a particle, a fermion which is its own antiparticle, does not have any charge. So this particle was these Majorana fermions was postulated and formed by Majorana. At that time, the Dirac equation was already well established, and Dirac found a solution of his equations, and he had some complex solutions, which means that psi and psi star were different, so there were particle and antiparticle. And all the genius of Dirac was to give some physical interpretations to the antiparticles, because at that time antiparticles were not found accidentally. And a few years later, actually just maybe a couple of years later, Majorana found also some different representation of Dirac equations, which is called the Majorana representations, in which the gamma mu becomes purely imaginary, such that I times gamma mu is a real matrices, and therefore the solutions you can write the Dirac equation in terms of only real numbers, such that the solutions of the Dirac equation are purely real. So therefore, using these Majorana representations of the gamma matrix, he can apparently find a solution which is its own antiparticle. So purely real solution. Verifying psi equal psi star. Obviously, this is a different solution of the Dirac equation. It doesn't mean that there must be a particle associated to it, but at that time, Majorana was postulating that it may apply to neutrinos.
Sorry, may I ask you, when you say Majorana fermion is a fermion, not in the statistical sense, in the fermion statistical
in the
sense?
anti-commutation relation sense.
So, what do you mean that when you say that Majorana fermion is a fermion?
But
Is a fermion?
I will come to that. Continue talking. It's it was introduction. So, just a few words of Majoranas. Most probably you have been introduced to Majorana by Rosa before, and this is the typical slides we show. So, if you have not seen the face of Majoranas, well, it's difficult to avoid these days. So Majorana was Italian scientist. he has a very short career, and he makes several contributions. One of them being certainly this purely imaginary representation of the gamma matrix. As you may eventually see, all these gamma matrices are purely imaginary, such that I gamma is real. And Majorana is known more for his fate. Actually, he disappears when traveling from Napoli to Sicilia, and soon after he published his famous paper. Actually, the story is that he even did not write the paper. Fermi asked him, "Can I write for you this paper?" So Fermi wrote the paper, this famous paper. This is not yet, and he didn't want to publish because it seems too easy. I mean, technically, algebraically speaking, it's just a change of unitary transform, just a change of basis, if you want, in terms of gamma matrix. But it has deep consequences. So, especially for condensed matter physics, and this Majorana quasi-particle could be very interesting and stimulating because they have some non-abelian statistics. So, unlike fermions, they obey non-abelian, so therefore and these non-abelian statistics can eventually be used for quantum computing. So this is one main reason condensed matter physics are pursuing this toward this Majorana business. So the race is on, and still there are some more experiments going on. So let me, to answer your questions, let me explain what I mean by Majorana fermion in condensed matter. Majorana fermions, first, in condensed matter, they are not genuine particles, they are quasi-particles, so they are emergent excitation, if you want, in solids. And they obey non-abelian statistics, I just emphasized, and this is interesting for quantum computations. So they are ordinary. I didn't mind that they are fermions in the sense that they do anticommute, so this is the anticommutation relation for ordinary fermions. And how could I define my Majorana fermions? I just decompose the standard fermionic destruction operator as gamma plus I gamma. So gamma 1 plus I gamma 2, such that obviously the gamma verifies gamma star equal gamma, so let's say it means that creating or destroying the Majorana fermion is the same in this sense, and they do anticommute. That's what I mean by fermion. That's this second quantification definition doesn't. You can say just a different representation, if you want, of a creation or annihilation operator. Once you wrote that, it means that you can recast any fermionic Hamiltonian in terms of Majoranas. Once you have done so, you have not done much. I mean, just a rewriting of any fermionic Hamiltonian. So, what's the deal? The idea is that indeed every fermionic Hamiltonian can be recast in terms of Majorana operators, just a change of representation if you want. But very few Hamiltonians can support solutions with isolated localized Majoranas fermions. And that's these isolated localized Majorana fermions are what experimental condensed matter physicists are running at, to find a system in which you can have some isolated excitations, something you can eventually localize and manipulate, do something with it. So this is the second quantization version of what would be a Majorana fermion. So where to look for Majorana fermions? It's a good playground is to look at as a collective excitations in solids with unconventional pairing. So it should be an excitation which is its own anti-excitations. So therefore, clearly looking for superconductor is a natural way. Why? Because in superconductors, these Bogoliubov quasiparticles have weight as a superposition of particles and holes. In other words, the Bogoliubov quasiparticles is the sum of creations and destruction operators. The point is that for standard S-wave superconductor, as we all know, I mean, an S-wave is composed of correction with spin up and destruction with spin down, or vice versa. So therefore, if you take the emission of this gamma n star, there is no way you could have the property that gamma star equal gamma because of the spin in green here. So if we are to look in terms of quasi-particles and superconductors, the superconductor must be quite strange in the sense that it must have some unconventional pairing in the triplet sector. In other words, it's like you should have some kind of superconductivity with polarized fermions. So here, imagine that you have some kind of spinless or polarized fermions in the sense that you only spin up, and you try to build some quasi-particles in terms of this A dagger up and this A up. Then you have a chance, taking the emission of this operator, to have gamma equal gamma star. And in particular, if you look at zero energy, this operator does satisfy gamma star equal gamma. So good place to look for these minor fermions is first to look at superconductor with unconventional pairing. We call it triplet. The simplified version of the triplet is the one in which all the electrons have the same spin, if you want. The point is that these triplet superconductors, a priori, they are not that easy to find in nature. There are a few compounds, a few superconductors which might be in this, might have bear this anomalous pairing. Still, I mean, the situation is rather controversial, I'm thinking. So the deal now is okay. Two roads. Either first road is to look at to find new material with unconventional pairing and hope that they can have some Majorana excitations at zero energy. The second strategy, is maybe, which I will come to it later, is to manufacture some effective unconventional superconductor. So a famous example of this P-wave superconductor was given by Kitaev in a 1D toy model. So the idea is that you decompose your creation destruction operator in terms of two Majoranas, just a change of representation if you want. So this is what he did here. He described two. So imagine you have an operator at side G, and you decompose it into two Majoranas. So this is just a rewriting, if you want, of some chain. So I insist there is no spin in there, or all the electrons have the same spin, if you want. So usually this is what you do. Suppose you invent some process in which you can pair electrons in such a way, then what you hope is that you will have two isolated Majorana fermions at the end. So you have to find the right glue such that there is some pairing between the electron and its nearest neighbor, G plus 1, and therefore at the two sides you will have some isolated Majoranas. So through this simple 1D example, you see that the Majoranas only appear at the edge, so they are 0D objects, they are localized objects. So you have to find, and what Kitaev shows by a simple toy model, which I did not write, it's easy to realize such situations. And what could be useful for, is that once, providing you can realize such P-wave type 1D superconductor, you are left with isolated Majoranas. And therefore, it constitutes an ideal platform for quantum gates. So since this proposal, there have been many proposed realizations. So I won't talk about this morbid fractional conjugal effect. So spin-polarized P plus IP superconductor, it's triplet superconductors, but nobody has found in the literature, in the nature. The idea is also to use a topological insulator and to realize some interface between topological insulators and standard S-wave superconductor. Also to use semiconductors with strong spin-orbit coupling plus some superconductivity plus magnetic insulators. And this list is still non-exhaustive. I will mainly focus on this last point. So the geometry I will be talking about and as a proposed realization, which is the one which is mainly currently investigating experimentally, is this one. Imagine you have a semiconducting wire with strong spin-orbit coupling. You have some external magnetic field, and you put it on top of an S-wave superconductor. So why this proposal is rather successful, because all the ingredients are already available. Condensed matter experimentalists are very much used to deal with these semiconducting wires, S-wave superconductor, so all the ingredients are available these days, and actually experiments have been already done. A few results which I will mention. So this is the outline of my talk. I will show you why this geometry can indeed realize 1D topological superconductors, and then I will try to. I'm not sure we have time to cover all these topics. I doubt actually. I will show you a few recent results in a group where we obtained within this geometry. So if you have any questions or something which I'm pleased to hesitate then. So what do I mean by 1D effective topological superconductor? So the idea is to consider just the bond structure of a quantum wire. So let's consider this, for example, indium arsenic nanowire or indium antimony nanowire. And I will assume, consider one band only. So what are the ingredients I need? So this, I assume single channel, as I said. I assume a strong spin-orbit coupling. Here it's of Rashba type, but some other types could be available. I need some Zeeman splitting, which should be rather strong. And at this level, what is the band structure? What spin-orbit is doing, without the spin-orbit, without the Zeeman, you would just have a parabola, so k-squared of the 2m dispersion relation. Spin-orbit is giving the spin degeneracy, and you have two parabolas instead, this here and here. The spin is no longer a good quantum number, only at very large momentum that you can associate your spin to this large momentum here, let's say up here and down here. In the middle, it's mixed, and if you add the Zeeman split, Zeeman term, what the Zeeman will do, it will open a gap between these two. And therefore, instead of these two shifted parabolas, what you will get is you will get the first band and the second band here. So, obviously, these nanowires are interested because they can, if they have a large G factor, and with this large G factor, it means that the Zeeman gap would be rather large. And the point is now, what happens if you fine-tune your chemical potential right in the middle, in the middle of the gap? Then you are left with effectively a single channel, single band. So at this level, I've not yet mentioned any superconductor. So now you put your wire on top of this S-wave superconductor. If you fine-tune your chemical potential, that says here, for example, then you have three types of effective pairing. I labeled my band by this plus and minus. You can, so the lowest band will be minus. You can have effective pairing between minus minus or plus plus or minus plus. This is the standard case. But if you fine-tune your chemical potential right in the middle of the Zeeman gap, and providing your gap is large enough, the only effective pairing you can get is through this minus band. So what you have effectively realized is that spin is no longer a good quantum number, but this, let's say this minus is your new quantum number. You effectively pair electron with this good quantum number. So you effectively create some kind of triplet pairing between electrons with the same label, if you want. So instead of working with elusive triplet superconductor, you take ingredients you know well, you manufacture, and you create some kind of effective triplet pairing. In the sense, the triplet will be in this minus sector. So that's the strategy which is now these days followed by many horizontal groups. And so what is the main predictions? Is you need, to get this effective triplet pairing, you need a substantial gap, Zeeman gap in the middle. So indeed, what you want is that the Zeeman gap must be larger than the effective pairing gap. Appears it's not obvious because magnetic field and superconductor do not like each other. Typically, a magnetic field will destroy very easily the superconductivity of the S wave. So the point is that what we are interested in is Zeeman gap. And Zeeman gap, there is a G factor that comes into play, and you need a material with a large G factor over there, such that you have a large G factor which will be induced in the semiconducting wire. So, we have a large Zeeman gap induced in the semiconducting wire, but a very poor Zeeman gap in the S-wave superconductor. So it's a balance. And when these recipe, when you have all the ingredients and when all these conditions are met, what you do realize indeed is some effective triplet pairing, and you have the right recipe to get Majorana fermions. And so the condition is that indeed, assume that mu is 0 in the middle, you need that the Zeeman gap being larger than the superconducting proximity gap. And if this is the condition to enter into this topological phase, in which you do expect some mid-gap states, which are Majorana fermions. So here, you see when you enter into this topological phase, you expect that to have two Majoranas at both ends of the semiconducting wires. So many, up here you can use many, what you need, it actually is some semiconducting wire with a strong spin orbit and a large G factor, fine. So indium antimony is a candidate, also indium arsenic. Carbon nanotubes have also been emphasized, and some wires made of topological insulators. I mean, this list is as a non-exhaustive. I want also to sell this point. I mean, what you need actually some kind of helical ordering. By helical ordering, it's some kind of it's what I try to represent here. And I want to emphasize that also in wires, nuclear spins do provide for free this helical ordering. So I was saying that you need some spin orbit and Zeeman. Let's change the frame. Let's go into the frame, the spin orbit frame. The spin orbit frame, what you see, you follow the spin of your electrons. Okay, and so if you follow the spin of your electrons, the fixed Zeeman term will stop being just rotating. So from just the change of frame, in the change of frame, if you go to the spin orbit frame, what you need some kind of rotating magnetic field. So rather than so you could, what I'm saying, you could imagine having a semiconducting wire without any spin orbit, but having some kind of, you have some rotating magnetic field around. By, I don't know, you have to invent some magnets such that the field is rotating. That would be fully equivalent to fixed Zeeman, fixed magnetic field plus spin orbit, just a change of frame. And actually, what we found recently is that the nuclear magnetic ordering is providing some over the field, which is spiraling, And this is fully equivalent to the spin orbit plus Zeeman. But here, you get it intrinsically for free, do nothing. So no Zeeman, no Zeeman. So it's just a gauge transform if you want. So if I put, I won't go, the point is, we predict recently that this, some nuclear spin ordering should occur at very low temperature. Unfortunately, this is very low. But if people would realize the geometry, then you could expect some Majorana fermions to occur at very low temperature without any use of spin orbit or Zeeman. So this is science fiction, since nobody has seen that. So on the other hand, going back to reality, there are many experiments these days working with wires plus on top of superconductors. So these are at least I denoted at least 4 experiments. The most famous one is the Kuvan group. So this is the sample that you have. You can see the wire here in white. This is the superconductor. So the wire is indeed, part of it is on top of the superconductor. The wire is made of indium antimony. It's indeed a large spin orbit. It has a very large G factor, you have 50. And you have the Zeeman. So all the ingredients are there. And they do what they did. So the prediction is that if below the superconductor, there should exist some kind of Majoranas. It's the red star here. And they would have some signature in transport, and that's what this group has been probing recently, some anomalous transport feature. Similar geometry with indium arsenic wire were done in the Weissman group, which are very controversial, as Ravon can comment on.
Yeah.
And there are other ongoing experiments in Lund, in Purdue, and okay. So the race is on. Unfortunately, I won't show you any Majorana fermions these days because the results are still controversial in the sense that the interpretation is far from the one-to-one. And you can find many other excitations not related to Majorana fermions which could provide some anomalous transport features. That's where people are. Still, progress is fast, and maybe in a few years or months, there might be some non-trivial business. So this is the real matter. So, and I will. So here is a few questions I will try to answer. So when we enter this business, we ask ourselves a few questions. First, how can we characterize locally these Majorana fermions? Can we find some kind of local order parameters treated to this? And we came with a solution in terms of what we call Majorana and spin-polarizations, which are to give you the feeling. So the idea was to find a quantity which would be analogous to kind of a real spin. So I told you that general wave functions, Majorana is a superposition of electrons and holes. So U C dagger plus V. So the idea would be to use these simple decompositions and define the quantity that. So when U equal V, this would be some Majorana of type up, and when U. So I use this simple decomposition and I define a quantity which. So it's a first quantization, and whatever wave function I have, I decompose in terms of the number of C dagger plus C and number of C dagger bits. So I define this quantity, which I define, which are the U plus V squared divided by 2 and U minus V squared divided by 2. And I define my Majorana polarizations as the difference between these two quantities. I do that by pure analogy with some kind of spin, if you want. So it's the degree of admixture between particle and all. What I want, Majorana is perfect equal degree of admixture between particle and all. So it will be in the middle. You can another way in terms of second quantizations. This quantity would be the local it will be some kind of proportional to the anomalous triplet pairing. So you have in second quantization language, you can define some anomalous triplet pairing. It's an operator. And this Majorana polarization measure locally the anomalous pairing, which in other words, locally measure the admixture between particle and all of the same speed.
You said before that in order to have gamma equal gamma permission,
yes,
you have U equal V.
Yes.
U equal minus V, you have gamma equal minus permission.
So it's not only U equal V, you have also U. Look here, where in the beginning I have that. When you see that when you write your Majorana your electrons in terms of Majorana fermion, you can define two sorts of Majorana fermions. So actually, I should have added some gamma plus gamma 1 plus I gamma 2, and you can also, there will be the gamma minus I gamma 2. There is some arbitrary phase. So it's U equal V in absolute value, yes, but there is a phase. What can this quantity can be used for? First, as I emphasized, it's really the mixture of measure the mixture of particle, or more specifically, the degree of P wave type effective superconductor. It's a local quantity, and at zero energy, it's you can prove it's actually maximal, and it predicts the existence of Majorana fermions. So therefore, it can be used as a local order operator. The whole point, it's a local quantity in the sense that it allows you to explore locally the structure of the wave function, and also it allows you to define, by energy with spin up and spin down, the two Majorana fermions, which are so it has some cover if you want. Fine. So in practice, so take a wire, so it's tight banding version of a wire. And this is when this topological condition is satisfied, this is what you get. So this is the length of your wire, it's a tight binding, so number of sides. And you have these red and blue points are associated to my Majorana wave function. They are indeed at zero energy. And you see that you may eventually have some, it's not, at finite energy, you can also have some structure. It doesn't tell you that it's Majorana, just have some particle all overlap. Anomalous pairing. It's only Majorana at zero energy. But it's really, completely speaking, it's really a local measure of anomalous pairing. That's it. And, okay. So and the whole point is, it's a local quantity. And indeed, you can use it as an order parameter. So if, for example, this is the energy as a function of Zeeman gap, and you need a substantial Zeeman gap to enter into the topological phase. So you see that for Vz equal 0.3, then your states goes to zero energy. And here you know that at zero energy, these Andreev states, is Majorana fermion. So what happens for quantity, which we do by Majorana polarization, indeed, when you switch on the Zeeman field, there is nothing until 0.3, where you saw these two Majorana fermions appear. So this Majorana polarization is really switched on right at the transitions, and before it's fully. Yeah.
But if you plot the density, you will see that you have
same.
States.
So what compared to densities, yes, there is one more information here: color. Okay, blue and red. That's it. And this is useful. It's easy in type degrees of freedom, which you have more. Density of states will give you the same. I agree. But color is useful. We understand why later.
Sorry, up and down directions are physical directions? Or
No. Not physical. This is some kind of measure of parity in the system. It's not genuine spin.
It can be up and down in any direction in space.
Yeah, I mean, my Majorana wave function is a superposition of electrons with up and down. So there is a C dagger up, C dagger down, C down. So the spin, forget it. I will come to it later, but up and down is maybe, Ising lag is maybe misleading. I mean, well, I prefer to go in blue, and it's really related to the parity.
It's Ising in the parity language.
It's Ising in the parity language. MTO. Okay, so fine. I mean, I would say that. So what's the deal? As Josephson, plot density of states we have the same. Okay, fine. I fully agree. But now we by any chance we calculate this minor polarization, and we also compute the spin, the electronic spin polarization. So we're talking not about this time about some genuine spin polarizations, the one you would like. And this is what we obtain. And we do obtain that the x-axis spin polarization, which would be orthogonal to the direction of the Zeeman field, behave almost similarly as my Majorana polarizations. Not almost, actually, very, very similar. You cannot distinguish from your eyes. And this is something people can approve. Spin polarization is a genuine physical quantity people can measure. And how come? Is it the fruit of a choice of parameters? So we tried also with disorder, and indeed, for Majorana polarizations, x-axis spin polarization almost the same. Okay, I think there are differences, but at least it means that if this is true, and I do believe this is true, at least, is that you do have some signature of this Majorana phenomenon in the spin sector. And to do so, we also do some analytical calculation, the continuum limit, and we indeed find that this electronic spin polarization is related to these Majorana polarizations. And the whole point is that the electronic spin texture is maybe potentially be probed experimentally. So obviously this is only in the electron sector. So you would need some kind of polarized STM locally, which would be able to probe the electron sector. Total polarization is 0 because this is orthogonal to the Zeeman field. So if you probe the polarization in the hole, it would be opposite. But you would be sensitive. You would need to measure some electron spin texture, let's say, and this could be in some way to probe these minor phenomens. Also, another way which we could discuss, you can bring quantum dot nearby the edge, which would be sensitive to these spin directions, and that's something we could discuss afterwards. And you would ask me, why is this relation? Why there is some relation between Majorana polarization and electronic spin texture? I mean, the most important message here I want to convey is that there is some physical signature associated to this Majorana in the genuine spin texture. There is no Zeeman effect. I mean, so because there is no charge, there is no Zeeman effect associated with it, but there is a natural spin texture associated to it. Sorry, I won't answer this question because I don't have the answer. Why is this relation? Put a question mark. There was a recent paper where they probed some very nice duality between particle hole and spin degrees of freedom. Since my Majorana polarization is really some kind of local mixture of the particle hole, I mean, it's a local measure of the particle hole mixture, I was thinking naively, okay, using this duality, that's why there is some indications, but unfortunately it's not that simple. There is no one-to-one. It does not work. So maybe, at least I didn't find a cute path between these two. So, I'm sorry. I don't have any explanation between just some hint. So, still, the effect is there. So, I'm trying to convince you that this color, this can be quite useful to analyze more complex hybrid structure. So, especially to analyze the interplay between Andreev bond states, which do occur in every experiments involving superconductors and normal metal or insulators, and Majorana fermions. So I will analyze the rest of my talk, SN and SNS junction. How much time do I have actually? Yes.
20 minutes. 20 minutes.
Really? Fast.
Yes, I mean,
Or 5?
It's
5?
10. 15.
Okay, then I mean,
I mean,
because I have enough material for 2 hours, so don't worry.
20 minutes including questions.
So, what is the NS junction? I mean, this is the idea is as the Kuhn-Oven experiment I showed you before, you put your wire on top of a superconductor, so part of it will become topological, part of it won't. So we analyze this kind of geometry. So it's called an SN junction, superconductor normal. And so what you expect? You expect to have one Majorana here, and eventually one Majorana here. So is it what you found? You look at the local density of states, you indeed find one Majorana here, but where is the other Majorana? You would expect it to find at the edge here, but no. There is no Majorana bond state and the interface. What you indeed find is that, and you do expect, because there is no single Majorana. Majorana always come into pair because they are created from electrons. And indeed, the other Majorana is fully delocalized and it is here. And we plot by minor polarizations. So you have, for example, it's blue here, it's localized, and the other is fully delocalized over the normal part and point. And the integral of this guy is exactly compensate this guy. So you need to find the two Majoranas, and the minor polarization is concerned. So the main message is that this Majorana can be delocalized, which could, I don't know whether it's this could be also it's kind of good news. It means if they are delocalized, they are easier to probe. You don't need to. And also, if they are delocalized, they are easy to project and to move. So that's and this picture has been confirmed by extensive analytical calculation. This is a superconductor. And this is the normal part, and this is the superconductor. And indeed, this is the Majorana wave function. It's fully oscillating and delocalized over the whole normal part. That's what's found in this paper. So in perfect agreement with what we found. So the main output of this Majorana-Andreev state is that they are very robust. They are really pin at zero energy. So you can move the chemical potential, move the Zeeman effect. Providing you are in the topological phase, they don't move. While Andreev states, which are also superposition of particle in all, not balanced, they do oscillate. They do have this type of behavior. Here it's desperately and perfectly flat. So they are easy a priori to detect spectroscopically.
So what are you plotting? Density of?
So here it's density of states as function of energy and the chemical potential. In these plots, previously I considered some sharp boundary between some. You can also wonder what happened if you have a smooth boundary, a soft boundary between them. So if you have a proximity-induced gap which smoothly decreases into the normal part, that's what. So here, this is a rather already soft. The Majorana is less localized, but if you can cross over, if you can imagine if the proximity-induced gap decays and eventually covers the whole the whole normal part, what you will find, you will fully localize your Majorana into the wall. So essentially, your normal part becomes superconductor. Yeah.
You're talking delocalized because you say these oscillations are the wave function.
Yes.
The Majorana polarization.
No, I'm talking about what I showed you before is really the Majorana wave function. And what in my previous sample, I told you, look, if I have a topological wire, the Majorana should be at the end, should be therefore localized. What I prove you, this is not true. Majorana can be delocalized. It's not obvious to have localized. despite you have all the basic ingredients, the output is that you don't get it for free, the localization of your minor wave function. It indeed gets spread and be fully delocalized into the luminal poles. That's it. So you have to pay attention. Is it bad news or good news? I don't know. There are some advantage. They are easier to manipulate, but they are not always localized. That's it.
And then how do you calculate this wave function?
Solve. It's an eigenvalue problem, and that's it. You have to really, how to do it. It's not easy, actually, technically speaking. Really, you have to solve your volume of the Eugen eigenvalue problem, analytically speaking.
The basis of
No. You have to find a cute basis, and actually you can only solve it analytically at zero energy. But it's really a matching of boundary conditions between superconducting and normal port in the spinor language.
So if I understand correctly, your conclusion is that a Majorana mode or state is not really an edge state, it can be bulk state?
It can delocalize into, yes. As soon as it couples to some kind of continuum states, it
doesn't really need an interface or an edge.
You need, here I do have an interface. I would have expected to have a Majorana localized here. This is not what happens. It localized.
Yeah, you write polarization.
Yeah, but Majorana polarization, wave function, whatever, this behaves similarly. This is fully
It's
equivalent.
not the same, no? Because in this oscillation, when it's zero, it's either U or B are different.
I could plot the density of states, which is plotted here, or the square of this is essentially the density of states, and that's what you would observe. It's delocalized. That's it. It's the same. What you get in more is, essentially here I should have the same. Here it's negative, it's positive, so you have two color code. But in terms of delocalization, this is the same piece of information. And this period, it's real space, it's 2K. It's essentially given by the Fermi in the normal port.
Sorry, a question. This extended state in the normal part also have the same Majorana polarization that in superconductor part?
Yes, it's conserved total. So this okay, same behavior here. Maybe I want to mention this. So we also use this probe, this SNS junction. So what to expect? So SNS means that you have two. It's like you have so your wires is on top of two superconductors. You expect when the topological condition is met to have two Majoranas here and here, and two here and here. So total is 4 Majoranas. So, and this is what you get. You have these two Majoranas here, but the two, actually they do split, and you have only two Majoranas, and right in the middle you have some kind of delocalized Andreev states. And this was obtained when the phase difference between left and right wire is zero. The phase, so you have two superconductors with the same phase here. And what gives you more is the color. Here's blue, here's red. That's an indication. That's something which was not included in the local density of states. So in this sense, this is useful. And if you switch on the phase and have some pi phase difference, that's the color are what you do observe. These two Andreev states here, they fuse and become, here what you see, by putting the local density of states on Majorana type of density of states. But the Majorana polarization gives you something more. The color is interesting. Before it was blue and red dot. Now you have two blue dots, and in the middle you have some red dots. So it tells you that the parity of this Majorana change rotates. And here instead you have creating you have created two Majorana fermions here. So total Majorana operation is conserved. It's, let's say, it's -1/2, -1, +2 if you want. So in this sense, the color helps you. Otherwise, without the color, you really don't really know what you have. And that's.
I would say this is equivalent to this picture of the fraction and Josephson effect, because you conserve parity. You have this fractional Josephson effect. In your language, you conserve parity, and hence you should change color of the Majorana polarization.
It's pretty cool. And so we plot these things as a function of flux, and you see the rotation of my polarizations. And it proves that indeed in the middle you have two Andreev states which fuse into two Majoranas. And this is difference as a direct application of it is the anomalous Josephson effect. If you have a trivial phase, so what you expect, some avoided level crossing, instead, if you have a topological phase, this crossing is protective and you get a 4 pi Josephson effect, which is related to that. Simple explanations, which you can write an effective Hamiltonian between these two Majoranas. You assume this is to be infinite, and indeed, this effective Hamiltonian, you can see that I gamma 1 gamma 2, some kind of tunnel Hamiltonian between these two Majorana fermions, and it's related to the parity, which is a concept quantity. So this crossing is protected by parity symmetry. Okay, I won't mention that. We played recently with a Josephson junction involving multiple Majoranas. So this may occur for wider, not too thick, with a few channels. This is for you, Rosa. You know, it belongs to BDI class. It's private, sorry. We play with it, and the question we're wondering is, if you have many more Majoranas, do they recombine and do they kill this Josephson, anomalous Josephson effect? So we checked with fixed models, with tight binding models, that indeed, and we wrote some effective general Hamiltonian. And what we do found is that indeed, the level crossing is protecting at 5 pi, and you can label all the eigenstates. And the idea is, if you have 4 Majoranas, you have 2 fermions, genuine fermions. And you can always combine them into 2 genuine fermions, and therefore you can label your avoided crossing by some parity. So parities can be even odd, and you have 2 fermions, so you have 2 quantum numbers, so you have 4 labels, 1, 0, 0, 0, 1, 0, 1, 1. And if you can label all your eigenvalue with this one, then they are protecting when they generated. And this is this parity which protects you from, which protects these anomalous Josephson effects. I think I don't have time to do that. And with that, I would like to summarize what I did. So I tried to convince you that there is a general playground with spin orbit plus Zeeman magnetic field and localized Majorana fermions. That this Majorana operation can be useful to see especially the fusion between Andreev states into Majorana business, into Majorana fermions. And something which I want to insist on is that there is some genuine quantity, and there is some genuine spin texture associated with these Majoranas, which could be something that could be experimentally available. So you need some polarized derivative. And there is a strong interplay between Andreev states and Majorana states in SN and SNS junctions. I did not cover these last 2 points, so I have to thank you for your attention. And last, thanks to my collaborator. So Doru, he was my PhD student. He is now a postdoc in Dresden, with whom you have a common program, as far as I saw the corridors. Denis Chevalier is a postdoc, and he will move to Leiden with some other group working in Majoranas. And Christina Benard, she's just moved to IFISC. Thank you very much.
Now it's time for questions.
I have a question for you. Can you put this slide of this 4 pi effect? And or the previous one with the Majorana polarization.
This one?
No, yeah, this one for instance, or the previous with the Majorana polarization. The other one, yeah, this one. Really. So as I said, I mean, this Majorana polarization, this change in color can be related to this crossing at pi due to this parity conservation of the fractional effect.
Yes.
So my question is, as you know, we've been studying this fractional effect in real junctions, when you have a finite length, and when you have quasi-particle poisoning. So in such case, there is no parity conservation. It means that you don't have a fractional van der Waals effect. Sorry, fractional Josephson effect. Correct? So my question is, what would happen if you study this Majorana polarization under the same assumptions of a finite length?
I would expect us this avoiding crossing.
So the question is this Majorana polarization robust against finite length effects or quasi-particle poisoning?
Finite length? I'm sure, because there is finite length.
But I mean, finite length not of the SNS junction, but of the nanowire itself. Then you would have always 4 Majoranas instead of 2.
Yeah. That sort of quasi-particle poisoning. It's a good question.
Because as we mentioned, this icing, this color is just an icing variable, which is parity. So if you have quasi-particle poisoning, how robust is this Majorana?
I'm afraid that with quasi-particle poisoning, I won't put my hand. I would expect it not to be robust with quasi-particle poisoning. It's a good question. As you say, it's. I'm not sure what trust. Also, interaction. This is a common interacting system. Interaction. No reason to believe. So, suspecting.
Yes, I don't understand your suggestion of extended Majorana states, because these would be like propagating Majorana states, as I am
Delocalized.
But somehow at zero energy.
Yes.
But this is forbidden by Bloch theorem when you compute the bands, the band structure of the Mount system with this Bloch theorem. There is a gap, so there is no possible Bloch state
I'm breaking
at zero energy.
Sorry, first here it's a finite size. The normal part is not infinite. It's finite size, so.
Okay, so it's not really extended.
No,
it's in a finite size.
Yes.
Okay.
It's like a bounded state.
It's a bounded
So
state.
you don't really know what is the effect of the other.
It's already, the normal part is finite.
Okay, so then I would not call this really extended.
Like a bounded state.
Yeah.
Has a finite width.
Finite system.
Okay.
Finite
Well, it's delocalized over the whole finite size normal
It
part.
has a finite width.
It has a finite width.
But if you could imagine making it longer and longer, then they would
No.
not go.
It would
up.
decay.
It would decay.
Okay.
Yes.
Because of the picture.
Must
Okay,
decay.
then I agree.
Must decay. It's not the finite. It's finite size, so there is no contradiction.
So there is time for last question, maybe? Yes.
A very simple one. How would you change this phase from 0 to pi?
Josephson current, for example. One way, one experimental way would be through how you change the phase of a superconductor. You need
With a squid.
a squid. Squid. So you have a squid below. That's there are a few experiments and people use squid geometry.
And in this controversy, you say that what people measure is not clear whether it's
They measure transport, and what do
this polarization? They are able to
no. Nobody is this polarization is a mathematical quantity or it's useful from a filter. What people are measuring is conductance or the IDV most likely. And what they found peaks. We all know that it's very easy to get peaks in the conductance.
measuring locally the spin spin-polarization.
No. So that would be something very interesting to do, but nobody is able to do that. First, it's a spin vector. It's a small. I mean, it's localized. It would be a small polarization. It's not a bulk thing. It's very. That would be difficult. Not impossible, but difficult. And as I said, there are some it's in the electronic sector. But if you do STM, you need to probe the electrons, not holes, mainly electrons. Not. It's doable. But